guys, and welcome back to my channel. Today I will be doing a video that I already filmed. It took me an hour to film, and then after it took me an hour to film, I realized that I never recorded it. But that's kind of been my favorite since I'm doing this video to study for a test. I just get to do it twice, so no hard feelings there. I'm going to talk about geography today. This is for my Geography 250 class. And we're going to start off by talking about some general geography. So, geography is the study of places and how they interact spatially to form patterns. For example, examining what's already there. Something that I didn't put on my notes here that I need to mention is that there is also physical geography and human geography. Physical geography studies the characteristics of a physical environment. For example, when geographers focus on climate, soil, / vegetation. This is physical geography. And then human geography focus is the study of human groups and their activities. So this is a social science, and it's like language and the building of cities. So those are some general geography terms. We're going to be talking about the contemporary approaches to geography. These contemporary approaches are area analysis, spatial analysis, and locational analysis. So here we're going to start with area analysis. So area analysis integrates the geographic features of an area or place. So essentially you're analyzing an area. Oops. This includes looking at data on a map and analyzing things such as how long it takes to get from one place to another with barriers. So let's say that this road broke over here and caved in, and so now you have a little water here, and so you drive to here and you take your boat to get to where you're going. This affects the area to where you're going. This is analyzing the area. Area analysis calculates distance and determines all variables that could impact a trade route. So this is an impact of the route. Right there. So that is area analysis. So under area analysis, there's also, you are looking at your site, situation, and concept of a region.
So site, situation, and concept of a region.
These three things are how you analyze an area. So the site describes the exact location of a place. This is like longitude and latitude. So we're going to use the Space Needle for example here. This is in Seattle. That is my Space Needle. Maybe it comes down like this and has a little like that. Just looks like a little UFO on there. That definitely looks like a Space Needle. Doesn't it have like... Okay, so there we have the Space Needle. So the site of this Space Needle is... So a site can be determined by longitude or latitude, or it can be described by characteristics. So let's say the food and the landscapes, there is buildings around the Space Needle, that's part of the site, and they speak English, that's part of the site. There's lots of traffic, that is also part of the site. So the situation is the location of a place relative to another place. So your knowledge of the Space Needle and where it's at will help you with your situation. So the situation, the space needles around these things. So with the site being an address, so exact, the situation is according to what's around you. Kind of like describing the situation. This is situated in between two buildings, a road, and some English-speaking people, probably some other languages as well, because it is a diverse city. That is your situation. The concept of a region. So we're going to talk a little bit in depth of regions here. So a region is defined by one or more characteristic or one or more distinct characteristic or features. Geographers actually decide what features are going to be used to describe a region. So there's three types of regions. You have a functional region. I'm going to actually, do we need this? We'll talk about three types right here. So you have a functional region. You have a formal region. So we're going to actually switch these around. With the three types of regions, you have a formal region, you have a functional region, and a vernacular region. We're going to start with this formal region here. So a formal region must have a specific characteristic common throughout the whole place. It exhibits central uniformity, meaning not changing in one or more physical or cultural characteristics. So we're going to use the mountains as an example. Let's say these are the Cascade Mountains. So these do not move. They are always going to be here. They are formally here on this land in Washington. So you have your mountains here. This is a formal region. Another example of a formal region is a country. Here we have, that's not how you draw it. That looks like a jelly bean. You have Africa here. And this is also a formal region. So this region is not changing. So Africa is not going to suddenly cut in half. These volcanoes aren't going to suddenly collapse this way. So these are formal regions. Next, we're going to be talking about a functional region. A functional region is an area organized to function politically, socially, and economically as a single unit. So we're going to use another country as an example. We're going to use the United States. That definitely looks like the United States right there. So this right here, USA, it functions socially and politically together to form a fully functioning region. The definition my teacher used was defined by interactions among places. So this United States interacts with Canada up here, right there, and it interacts with South America down here, I think it is. So this interacts with all the areas as formally, socially, politically, and economically. Next, we're going to talk about a vernacular region. A vernacular region is more as though like a sense of place. It is not bound down by any formal boundaries. An example of a formal region could be Eastern Washington. So here we have Washington State. That does not look like Washington State. Okay, we're just going to pretend that's Washington. So here you have Eastern Washington over here, north, east, south, and west. So your idea of Eastern Washington is up to you. it doesn't really have any clear boundaries. It's not like, okay, this right here is Eastern Washington, over here is not. You living over here in Seattle could say, oh, anything east of me, I consider Eastern Washington. So a vernacular region is a widespread perception of the existence with people within or without them. It doesn't really have any borders, as I said before, and it's more just your sense of place. But they're still, you can't just make up a vernacular region. It needs to be well known, obviously. We're going to talk about spatial analysis next. Spatial analysis. Spatial analysis is what it sounds like, analyzing space. We consider three things when doing spatial analysis, and those are density, concentration, and pattern. So these three things, we'll start with density. Density is the frequency of an occurrence of a phenomena in relation to an area. For example, population. So the population of the state of California is very dense. Everywhere you go, you are most likely to see a person. It is dense throughout the whole state, but another state such as Alaska, let's pretend this is Alaska, people in Alaska only live down here. So this is a concentrated density, and concentration right here. So this density up here is not very likely. Maybe there's some people building some igloos up here, doing some fishing, catching a little fish. But down here is where most of the neighborhoods and regular people live. So this is concentration. Concentration is the distribution of a phenomena, so this is obviously distributed very, not very dense, but this is the frequency, so this is very frequent. So your pattern is, for example, let's say you have a little road coming up here, and you have some driveways, and you have this pattern of one side here, skip a side, one side here, skip a side, for your houses. I'm sure there's a reason for this pattern here the geographers have decided, but this a pattern is the arrangement of objects geometrically. So that is where we get these. So the spatial analysis consists of density, concentration, and pattern. Concentration is examples right here. Density is the frequency, and pattern is the arrangement of geometric shapes. Spatial analysis emphasizes the interactions among places. So these are all interactions. People interact like this. People interact frequently. People interact concentrated. Before we move on, I'm going to be talking about a few terms here. First, we have community succession. So this is when the process of change in an ecological community. So let's say there's a house here, and this house catches on fire, and then pretty soon that spreads to all the houses. This community will burn down, sadly, rest in peace, and this community has now experienced community succession. This is the process of change in an ecological community. Oops, I spelled this wrong. This is change. Change to an ecological community. Next, we're going to be talking about biodiversity. This is essentially what it sounds like. You've got the diversity of biology. So an example of this would be like an ocean. So let me get my blue here. So you have an ocean. This is the variety of wildlife or plants in a particular habitat or ecosystem. So in an ocean, you essentially have your plants, seaweed here. You have your fishies. You have several different kinds of fish. I don't know how to draw any other fish. Maybe you have a little like poker fish thing down here. Got some coral. So this is a very biodiverse ocean. We're going to be moving on to volcanoes next. We're going to be talking about 5 different types of volcanoes. Stratovolcanoes, cinder cones, we'll see in a little bit. We're going to be looking at stratovolcanoes, cinder cone volcanoes, shield volcanoes, and calderas, and a lava dome. We're going to start by talking about a stratovolcano. A stratovolcano is kind of like most commonly found in the Pacific Northwest. It kind of looks like this, and it's called stratovolcano because of the layers of lava that falls. The lava that comes out of a stratovolcano is very high viscosity. Viscosity is another word for thick. So this is some very thick, maybe I'll add a Q in there. Thick. That's some thick lava. High viscosity. So that is a stratovolcano. So some characteristics is that it is steep and high in elevation. It is usually capped with a glacier. So some examples of this are Mount Rainier, Mount Adams, and Mount Baker. These are all steep and have high viscosity, thick and sticky lava. The flow that comes out of this type of volcano is very dangerous. It has a pyroclastic flow, which means that it has fire, rock, and gas. So you have fire, rocks, and gas. And the ash from these volcanoes goes a very long ways, such as the Mount St. Helens explosion. People experienced ash from that from a far away distance, so that produces a lot of ash from all the fire. Ash affects the air quality, so that is your stratovolcano. A cinder cone volcano kind of looks like this, let's say. It is a steep hill that can range in size for anywhere from 10 meters to 100 meters. A meter is 3 feet, so this is about like 30 feet to like 300 feet, something like that. A cinder cone volcano is a glassy volcanic fragment, and it is a downward wind from a volcanic vent. The characteristics include that it shoots lava and ash high into the air. So this is I always think of Nim's Island when I think of a cinder cone volcano. I feel like the island that she lived on had a cinder cone volcano just because of the way she looked into it from where she was standing. The volcano is made of something called scovia, which is like not very compact rocks, which is another reason why I think it was the volcano on Nim's Island, because she pushed rocks down the hill to scare the visitors off. So there you have your lightly compacted rocks, and this almost looks like a man-made dome here, and it has lava pretty much always bubbling in there. I don't know, that's just what I saw on Nim's Island, just running off of that. This lava is a low viscosity, so it is very thin. Low viscosity. And so it's runny and not very sticky. It looks like gray splotches on a map because of the rock buildup of the gray rocks. Next we're going to talk about shield volcanoes. It's called just shield volcanoes. A shield volcano looks like a shield, obviously. I mean, got its name from there. It's kind of like a dome shape like this, and you got your little opening here. This lava also has a low viscosity, so it just kind of runs out like this. It's a nice low viscosity lava. So this is a high viscosity, this is a low viscosity, and this is a low viscosity. Some characteristics is that it is runny lava, obviously some lahar. So lahar is, I forgot to mention with the stratovolcanoes, lahar is what falls down that volcano. It is mud. Well, lahar is another word for mud, but it is ash and glaciers or snow. Kind of creates a mud-like consistency. So here is your exploding shield volcano. It's not very steep, as you can see. The explosions obviously are not very high, as like the cinder cone and stratovolcano. Cinder cone is the highest. Stratovolcano is about medium, and this is a very low explosion. We're going to be talking about a caldera. Caldera, if I am correct, does not actually explode. So a caldera, let's say you have your cinder cone right here, and this cinder cone explodes, and this whole loose rocks right here, because it's made up of the scovia, loose rocks, breaks off. So now you have this right here, and you have a caldera, like that. So a caldera is a large bowl-shaped volcanic depression into there and it's the space left after magma has ejected during eruption, so such as the eruption of a cinder cone. We're on calderas and lava domes. Lava domes are usually inside of a caldera. Let's make that a little more baby-like. So here we have our little lava dome. The lava dome is a roughly circular mound shape of resulting from the slow extraction of viscous lava from a volcano. So it's just slowly exploding lava out from it, and it just kind of builds up here into a lava dome. So this lava is obviously very thick. It is highly viscous in such that it will create a dome shape out of the lava that comes out of it. It's sticky lava, it's less explosive eruption, so it's just kind of a consistent explosion, and lava domes are most likely in a caldera, as explained here. So that is it for volcanoes. Before we move on to earthquakes, I'm going to talk about endogenic versus exogenic. This is something my teacher did not feel explained very well. He overcomplicated it a lot. So I had to research it myself. So I'll use black here. You have your endogenic processes, and you have your exogenic. So these obviously are very simple. Once I realized, this is what I thought it was essentially, but then I got confused. So endogenic is what happens on inside the earth. Exogenic is outside the earth. So endogenic includes some slow movements. These slow movements can be compression and tension.
We'll learn more about compression.
Tension when we talk about earthquakes. And also some rapid movements or some sudden movements. These include volcanicity or volcanism, the process of volcanoes exploding, and earthquakes. Some exogenic things include weathering, mass movement, so some exterior mud flow from the earth, such as lahar, is a mass movement that's exogenic. We have erosion, and we have deposition, the depositing of things such as like debris deposited into and out of the ocean and such. So this is our endogenic versus exogenic processes. We just learned about this right here, and we will now be talking about earthquakes. Some endogenic processes. So as we talk about earthquakes, earthquakes take place along fault lines. So earthquakes take place along fault lines. There are 3 different types of fault lines. First of all, a fault line is a break in the crust. So it's a break in the crust of the earth, and it also shows plate boundaries. So we're going to be talking about the 3 different types of faults. We have normal faults, we have reversal faults. So if you don't overcomplicate these things, everything's fairly self-explanatory. My teacher likes to overcomplicate things and then I get confused. So this is a video for people with a simple mind, you know. They need to understand this geography. Also, I need to understand it myself. Writing it all out helps. So we're going to be talking about normal faults first. So a normal fault is when the earth's break in the crust. Sorry, I gotta let my dogs out really quick. Okay, so a normal fault is when you have a break in the crust that is pulling apart. So here we have our Earth's crust. And you have the center piece, which is falling downwards. And you have another piece of the Earth's crust. So this is going downwards, it's going upwards, and they are pulling apart. This is tensional, meaning pulling apart. Next, we're going to be talking about reversal faults. So, as self-explanatory as it can be, it is the opposite of a normal fault. So you have your piece of ground here, then you have a piece of earth falling downwards, and you have your other piece of thing here. So this is going downwards as well, and this is going upwards, and this is being pulled in, it's being pushed, opposite of the normal fault. So this is normal fault is being pulling away. This is pushing. So this is how it goes, like this. So it's being pushed in, and then as it is pushed in, this falls down into probably like the Benioff zone or something down here, which I'll talk about later, and it will create a earthquake. So an earthquake happens along those fault lines. The last one we're going to talk about is a thrust fault. I don't fully understand thrust faults. My teacher didn't fully explain it to us. But what he did explain is that it is kind of like a longer, kind of similar to the reversal faults, as it has like the same pushing. And so here you have your falling piece of land here, and then this, like this. So this is like thrusting over here, and this goes downwards and inwards and inwards and upwards. So that is a thrust fault. So next we're going to be talking about, first of all, friction helps indicate how strong a volcano is going to be. So let's, for example, I'm going to do a little thing here. So more friction / strain equals a bigger magnitude earthquake. for example, of tension, I just broke one of these, whoops. We're going to take a table. So this is why there's some earthquakes that are bigger or not. So let's say you have a little guy here, and he is pushing a table. You have your table here. And as he pushes it this way, and let's say there's a little like water bottle here. So as he's pushing it, he's pushing the top, but the legs are staying. So as he pushes this, the table goes away, but the legs create like, I don't know a word for it, they're attached to there. So this is creating tension and strain over here. So when he pushes it further enough finally, and the legs snap back, and they're finally straight again, and the table has moved directions, this creates a lot of friction between here to there, rapidly moving. And that is where you get your earthquake. So the more, and obviously this would rupture right there, and this would fall over, creating the shake in the earth. We're going to be talking about the subduction zone. Subduction zone earthquakes are the most severe earthquakes. So here we're going to be talking about, so we have the North American plate and the Juan de Fuca plate. This right here is the subduction zone. See, this plate is subducting into the ground. Here we have the Benioff zone. The Benioff zone is when the slab breaks down, the heat down in the earth, center of the earth, this heat breaks off a little bit right there, and then this falls in, and then the earthquake happens in the Benioff zone. But we're going to be talking about how tsunamis are made from this subducting plate. So the oldest ocean can be found along this subduction zone because, the oldest crust, because this is the Earth's crust going down into the Earth. So this is new crust created and everything, and it's being pushed down into the Earth. Here, how an earthquake happens and creates a tsunami is when you have your one plate here pushing against another plate, and the plate is being, this right here is stuck, and so this is bubbling up like this, and you have your water in here, and then when this plate right here snaps back out, and this comes up, you create a giant wave that takes over all the poor little houses right there into a tsunami. So it's a giant tidal wave, and it's the whole subduction zone in the area, so that's why a tsunami can be so big. The magnitude to create a tsunami is a 8.0 in the subduction zone earthquakes. Subduction zone first of all, this Juan de Fuca plate. Juan de Fuca plate is a portion of the Farallon plate, or Farallon plate, sorry. So the magnitude is to a 9.2. I think that, I'm not for certain, but I think the earthquakes that happen in the subduction zone are the strongest earthquakes. So this is the highest earthquake ever recorded, and this is the most common earthquake that happens in the subduction zone. The shallowest earthquakes in western Washington occur along the EW reverse faults. So EW reverse faults. So remember, the reversal faults are something like this, with the ground falling inwards. So this is where the shallowest earthquakes in western Washington. So they occur along the reverse fault lines of the Puget Sound region. So this is all the Puget Sound. So we live in western Washington in the Puget Sound area. So some features of the congruent plate boundaries are trenches and volcanoes. The sea floor, so here we have this. This is the sea floor right here. The sea floor provides clues about the location of plate boundaries. A plate boundary is like the ring of fire. Here you have a bunch of subduction zones, creating a bending off trench here. They help us determine the direction of plate movement. Plate tectonics, real quick, is driven by the convention of within the Earth's mantle and ocean currents. So that's all I'm going to be talking about today. Thank you for watching. We talked about general geography, earthquakes, and volcanoes. Hope you'll subscribe for more videos.